Okay, the next topic that we're going to talk about is when are two graphs the same or different? And as a motivating example for this, I've got drawn here two graphs G and H. And we want to know, are these the same graph? Or are they two really different graphs? And, well, at first glance, they certainly look different. They both have four vertices, but one of them has edges in the middle of this square of vertices that cross over each other. The other one has only one edge in this middle square and this other curved edge out here. And so they definitely look different. But the two graphs are telling us sort of the same relationships among the vertices. If I color code our four vertices, I will color them blue, green, red, and yellow. So in G, I'm going to make this top left vertex blue, this top right vertex green, bottom left red, and bottom right yellow. No, that is not yellow. Yellow. You can see that in G, blue is connected to, well, all three of them are connected to blue, and all three to green, and all three to yellow, and all three to red. And this is actually also true in H. And we can establish a correspondence by coloring the vertices in the same way. So I'm going to color this vertex blue, and this one green, this one in the lower left red, this one again in the lower right yellow. And you can see in this correspondence, blue is connected to green, red, yellow, blue is connected to green, red, yellow. Green is connected to blue, red, yellow, green is connected to blue, red, yellow. Red is connected to blue, green, yellow, red is connected to blue, green, yellow, and so on. The picture we've drawn looks different, but the information about how the vertices are related to each other is the same. And so we're going to say that these two graphs, G and H, are the same. And the word that we use for that is isomorphic. And the way that we establish that they're isomorphic is exactly what I did here with our coloring. We establish a pairing of the vertices. So we pair up vertices in G and vertices of H. So that paired vertices are connected in both graphs. And maybe I should say they're connected in the same way. And by that I just mean that I don't have two edges connecting blue and red in graph G, but only one in graph H. I have the same number of edges connecting each pair, or each set of paired vertices in G and in H. So let me give an example of a graph which is not isomorphic to G or H. Actually, we'll give two examples. So the first example is going to be, I'm going to call this graph G prime. And G prime is immediately obviously not the same as G and H, because G prime has only three vertices. So we can't pair its vertices with those of G or H. right? We'll have one leftover vertex in G or in H that doesn't get paired up. So there's no way that we can say that these two graphs are the same. So say this is not isomorphic to G and H. Okay, so number of vertices in the graph is the big first obstacle. But what if we have, let's take another graph that has 4 vertices. And now I want to check if this graph, let's call this one H prime. I want to check if H prime is isomorphic to G and H. Well, it's got the right number of vertices. And I could try to start pairing those up. For example, I could try, let's see, blue is supposed to be connected to everything else. So maybe I'll make this one down here blue. Green is also connected to everything else. So this one here can be green. Okay, but now I have a problem because no matter which of these two at the top I color red or yellow, we see there's a missing edge between red and yellow. Right? In G and H, all 4 vertices are connected to all 3 of the other vertices. In H prime, that's not the case. The red vertex and the yellow vertex are not adjacent to each other. And so this shows us that H prime is also not isomorphic to G or H. It's not the same, right? There's a relationship between red and yellow in G, which is not present in H. Now you might ask, well, what if I just picked the wrong labeling, right? Maybe red and yellow aren't the right colors to use up here. Maybe red and yellow should have gone somewhere else. Well, one tool that can tell us that, in fact, these definitely have to be different is the idea of a degree sequence. So the degree sequence of a graph is the list of the degrees of its vertices. We've got 4 graphs here, so I can write down the degree sequence for each of these 4 graphs. So G has a degree sequence of 3, 3, 3, 3. It has 4 vertices that all have degree 3. H also has 4 vertices that all have degree 3, so its degree sequence is also 3, 3, 3, 3. G prime has 3 vertices that all have degree 2. Each of them has 2 edges. So it has degree sequence 2, 2, 2, 2. And then H prime is maybe the most interesting of these degree sequences because they're not every vertex has the same degree. So you can see in H prime we have 2 vertices, red and yellow, that have degree 2. They each have 2 edges. And 2 vertices, blue and green, that each have degree 3 with 3 edges attached to them. So the degree sequence of H prime is 2, 2, 3, 3. And this helps us because, so we said kind of the first obstruction that we would have to overcome for 2 graphs to be the same is that they have to have the same number of vertices. Well, they also have to have the same number of edges, And they also have to have the same degree sequence. Right? Isomorphic graphs have the same degree sequence because they're the same. As a corollary to that, if my graphs have different degree sequences, like h and h prime, then they must not be isomorphic. They cannot be the same because this list of the degrees of their vertices are different. Another thing that can help us tell whether two graphs are the same or not is the idea of connectedness. A graph is connected if you can walk from any vertex to any other vertex along its edges. Say if you can walk between any two vertices along the edges. So we've seen lots of examples of connected graphs. I think every graph that I've drawn so far has been connected. If we look at G, H, G prime, and H prime here, you can see in G and H, it's very easy to get from any vertex to any other vertex because they're all adjacent. If I want to go from red to green, I just walk along the edge from red to green. G prime is the same way. Every vertex is connected to every other vertex. So these are in fact very connected graphs. H prime is a little more interesting. There are basically two cases here. If I want to go from blue or green to either other vertex, I just go along that edge. Now, but if I want to go from red to yellow or vice versa, I can't just walk directly from red to yellow, but I can still find a path that gets there. For example, I can, let me erase this pink. I could walk from yellow to green, and then from green to red. So it's still connected. I can get from every vertex to every other vertex. So what would a disconnected graph look like? Well, visually it looks like there's more than one piece of the graph. So for example, let's call this graph A. This graph A is disconnected. We've got this yellow vertex sitting out here by itself, and we cannot get from yellow to any other vertex. And that tells us this is disconnected. And we can also see from the picture of the graph that this has two connected components. Right? It's split up into two pieces where you can freely move around. Component 1 is just the yellow dot. Component 2 is the triangle. Another example. I've drawn here a graph B that has more vertices. This one has 10 vertices. And this has 3 connected components. And let's highlight what those are. So I'm going to highlight 3 sections in yellow, green, and pink. So component 1 is going to be yellow. And that's this set of 5 vertices. These 5 vertices I can freely get from any one of them to any one of the others. I want to emphasize that this place where these 2 edges cross is not a vertex. So even though these edges are crossed, we cannot get from this blue vertex, say, to this pink vertex. Right? There's no way to get from blue to pink. So yellow is one connected component. Then pink is another connected component. These 2 vertices are connected to each other, but not to anything else. And then finally, this set of 3 vertices off on the right is a final connected component. The 3 green vertices are connected, but they're not connected to yellow or pink. And so connectedness can help us because we can see that if we've got graphs that are connected differently, for example, if one graph is disconnected with 2 components, say A, that has to be a different graph from one that is connected with a single component, like G or H or G prime or H prime. These all have only one connected component, so they must be different graphs from graph A. B has 3 components, so again, it must be different from all the other graphs we've looked at. It also happens to have more vertices, but it provides an easy way to see that, for example, B is different from the graph C, which will also have 10 vertices. This graph also has 10 vertices, but it has only one component, so we can see that B and C are not here. I have one more edge to C. B and C are not isomorphic, despite having the same number of vertices. They are not isomorphic. Okay, and we'll stop there.